So it is a great pleasure to have Stéphane tell us about multifractal analysis of von Koch functions.
Okay, thank you, Hannah. Thank you, Thomas, for the invitation. So this is a joint work with Zoltán Bükzölich and Jan de Michel, who's in the room, if I'm not mistaken. So the starting point of this talk was actually a conference I organized 2 years ago, because I think at the time Jan was asked by some journal to write sort of a review paper on fractals or introductory paper on fractals. And so he read the original paper by von Koch about the snowflake, and he found something really interesting in it. And so that's what I am going to, I mean, besides the snowflake, right? And that's what I'm going to talk about in this alpha one. So at the time, so one important question was the existence and the search for continuous but nowhere differentiable functions. So you know that the first possible potential example was proposed by Riemann. And so it was a lacunary Fourier series. But actually, so you all know that this series, this one with the sign of n squared divided by n squared, is not differentiable at one or at a countable number of rational numbers. And then Weierstrass proposed his Fourier series, his famous example of continuous nowhere differentiable function. And then also Darboux gave another example, and Takagi also gave an example. And it's quite interesting that, of course, in this slide, we can see the curves, I mean, the graphs of the functions. But at the time, I mean, they had no computer, right? So they could not really see what the graphs looked like. In particular, if Riemann had a computer, then he could have guessed that his example was not a good one, because you can see at one that the function is differentiable, okay? And so when you read the introduction of this article, so there were two articles, actually, one in 1904, one in 1906, and if these two articles were nowadays submitted simultaneously to arXiv, then you would get a message that would say that there is a very substantial overlap between the two articles. But I like very much the introduction of it. So it's written in French. So I'm going to read it, but it was translated by Le Chat, you know, this French AI software. So you can read it, right? It's quite interesting. Until the time when Weierstrass invented a continuous function that does not possess for any variable determined derivative, it was a widely held opinion in the scientific world that every continuous curve possesses a tangent. But although Weierstrass' example has forever corrected this error, his example does not satisfy the mind, because the function in question is defined by an analytical expression that hides the geometric nature of the corresponding curve. So, and one would rather say that the appearance is in contradiction with the reality of the fact established by Weierstrass, right, in a purely analytical manner. This is why I meaning von Koch, right? This is why I wondered if one could find a curve without a tangent where this geometric appearance is in accordance with the fact in question. So the curve that I found, and which is the main subject of the following study, is defined by the geometric construction. So actually the main purpose of the article was not to introduce the snowflake, but it was to introduce a continuous, nowhere differentiable function, okay? But actually everyone only remembered the snowflake, essentially. No one went probably beyond like the section 6 or 7. So this is the snowflake. You know how it works, right? You take a segment, you cut it in three, and you replace the middle third segment by two sides of an equilateral triangle, and you repeat the process. So it means that every time you have a segment, you add a triangle whose height is a fixed proportion of the original segment, right? And you apply the process. So this is the Koch picture. But if you go a bit further in the article, then you can see the function, because of course the snowflake is not a function, right? It's not the curve of a function. And so what Koch did is that he studied this instead. So it's same kind of object, except that now it's a function. So what does he do? He takes a segment, and instead of adding an equilateral triangle, then he raises a triangle whose length, so you can see there is a length, so the height of the triangle is MD. So and he chose this length MD to be the same as the one he used for the snowflake, okay? And then he iterates the process, okay? And so at the end he gets this. Of course, this is not in original Koch's paper, right? This is what we get with the computer now. And what he proves using geometrical methods is that f is a continuous but nowhere differentiable function. Okay, but there are questions remaining. For instance, he left open the question of existence of points with infinite derivatives. And also now we can ask like more complicated questions like, what is the pointwise Euler exponent of such a function, the local behavior of a function? Does it have a multifractal behavior? Because the previous examples, except Riemann's one, the Weierstrass, Takagi, and Darboux ones, they are monofractal. They have the same exponent at every point. And so this is not the case for this one, as we will see. And that's my goal, is to try to explain. Okay. And so let's go back to the construction of the function. So because we're gonna generalize it a little bit. Okay, so we fix a parameter lambda, which is fixed for the rest of the talk. And so the construction rule is the following. So we have a segment that we cut in three parts, right? And each time, so it's AB. And to go to the next step of the construction, you replace the segment CE, which is the middle third segment, by two segments, right? Where the height of the MD segment, the central one, is a fixed proportion of the original segment. Okay, I think it's clear, right? So if you start with a horizontal segment, you get this triangle, just like the snowflake, right? But if you apply it a second time, then you get something different, which is still a function, right? But which is piecewise linear, right? And then you apply it to each segment, right? And so on and so on. And at the end, you get a function f lambda, because the sequence fn that you obtain is an increasing sequence of functions, so it always converges. Okay. Okay. So this is what we get for different values of different parameter values, right? So we have 1/2, 1/3. The parameter lambda square root of 3 divided by 6, so the red one, corresponds to the original Koch function, right? And then you have different critical parameters. Because what is quite kind of interesting with this function is that there is no closed form expression for f lambda, right? You cannot exactly write the value, or easily, in a direct way, easily write the value for f of x, okay? It's not a de Rham curve. It's not a solution to simple functional equation. It's not self-similar, right? And so all IFS methods cannot directly be used. And what is kind of interesting is that there are different phase transitions according to the ranges, according to the values of the parameters, right? We have identified at least 5 ranges, okay? And I will try to explain that a bit, okay? Any questions about the construction? Because if you don't get the construction, then the rest of the talk is a bit complicated.
So there's a chat message from Mihal.
Yes.
So he's asking about lambda AB or lambda pi 1 AB.
And that is, I'm asking, is this distance AB calculated in the horizontal direction or the geometric length of the interval AB?
It's the length of the segment.
Okay.
Yes, it's the length of the segment, not of the interval. So of course, and it's one reason for which it's not self-similar. Right? You can think about it, but it's the reason for which it's not self-similar. Okay, and so the first result we have, so with Jan and Zoltan, is that the sequence of functions converges uniformly as long as lambda is less than 5/6. Okay, and it diverges, so it converges uniformly, and it diverges for every lambda greater than 5/6, because even at lambda equal 5/6, then there are points at which the limit is infinite.
Okay. So there's another question in the chat from Maxime.
Yes.
Which is saying, what determines the angle between MD and AB?
The question is not exactly the angle. So you mean here, right? What's the value of the angle? The angle will depend on the original angle, because what matters is the length. It's the length of MD that is fixed and depends on the segment. It's not a matter of angles, it's a matter of length. Is it the answer?
But I guess you're putting M in the midpoint between A and B, and then the line segment from M to D is straight up, yeah?
Oh, yeah, it's vertical. Yes,
yeah.
It's vertical. Yes, sorry, if that was the question, it's vertical. M is the middle, yeah, it's the middle point between A and B, and MD is vertical, yes. Okay, so this is the first result. The second result is that indeed, when lambda belongs to 1/5 and 5/6, f lambda is a nowhere differentiable function. We guess that it's also the case when lambda is smaller, but we don't know yet, right? And also we answer the question by Fancor about the infinite derivatives. The set of points with infinite derivative has a Hausdorff dimension S, where S is the implicit solution to this equation, 3 to the minus S plus x minus S equal to 1. And so here you recognize probably the Hausdorff dimension of a contour set that you obtain by starting with a original segment, 0, 1, split it in 1/3, 1/6, 1/6, 1/3, and keeping only 3 of the intervals. Okay, so this is the first result. So and from this we can deduce a kind of important result somehow to justify our work, because is that this graph is not self-similar. Right? The graph of the function cannot be written, so it's compact, right, as a compact self-similar set. It cannot be written as a finite union of similar copies of itself. And just to give you the idea, it's quite interesting, because since the function is not differentiable, it does not have a derivative anywhere except where somehow it's vertical, right? And so if you have this equality between the graph, points with infinite derivatives must be sent to points where the derivative is also infinite, right? And so it means that the phi's, the angles, the rotation angles of the phi should be either 0 or pi. There are no other options, because vertical derivatives must remain vertical, right? And so the copy is either like a scale copy but smaller one with the same original direction as the graph, or a reverse version, an upside down version, right? And so then you can analyze the maxima and the minima of f lambda to get a contradiction, okay? And so this existence of infinite derivatives is yeah, quite interesting and useful, okay? So this is the, I would say, the first part. The second part concerns the pointwise exponent, like the local behavior of the function. Okay. And so for this function, all the exponents are less than 1. So the pointwise exponent is just given by the increments of the function. Okay. So we are interested in this pointwise Hurler exponent, which is the limit of the log of the increment divided by f of x minus f of x0 divided by log of x minus x0, right? And so our aim is to compute the Hausdorff dimension of the set of points having a given pointwise Hurler exponent, right? You fix h, and you look at the set of points having this h as exponent for f lambda, and you compute the Hausdorff dimension. This is the multifractal spectrum. And as most of you know, I would say, we most of the time expect for such objects like a concave shape for the multifractal spectrum because of multifractal formalism and theory and so on. Okay, and so before going further, I need to introduce some notations and some definitions. And Hena, you don't hesitate to stop me because I don't have the time. Okay, I don't see the time. Okay, so the interesting idea is that actually the behavior of the function f lambda around x is governed is given by the behavior of the orbit of x under the action of some dynamical system. Okay, and so the dynamical system is this one. So you consider this mapping T, right? So it's times 3 times 6 times minus 6 times 3, right? And so it has 4 branches. And so you consider its 4 inverse branches of T that I call S0, S1, S2, S3, right? And it's quite clear that this system of iterated function, I mean, consider the 4 contractions, it satisfies the open set condition, and its attractor is 0, 1, right? It's quite clear, right? You divide the interval into 4 parts. And so applying and iterating T gives rise to a natural partition of the interval 0, 1 in terms of the images of the 0, 1 by the 4 branches, right? And so I call IN, right? This IN here, the partition of 0, 1 in terms of the nth iterate of T, okay? And the important thing is that if X is any point in 0, 1, which is not an edge point for the function fn lambda, the intermediate functions that lead to fn, then there is a unique coding of X, right, in terms of this dynamical system, in the sense that X belongs to a unique interval, I, X1, Xn, right, that you obtain by applying, so here it's the mapping, right? So if you have I, X1, Xn, it's the interval that you obtain after applying Sx1, Sx2, Sxn. So it's a very small interval whose length is a power of 3, power of 6, right? Because this is the thing. So the important thing is that every X has a unique coding in terms of this dynamical system. And once you have a dynamical system, then it's, I mean, in this context, we introduce the natural self-similar measure associated with this dynamical system. Okay, so you take a probability vector P0, P1, P2, P3, and consider the unique invariant measure associated with the probability vector. So how does it work, right? It means starting from an interval of generation n, you split it in 4 intervals, right? The first one has length 1/3, the second one 1/6, the third one 1/6, the last one 1/3, and you distribute the mass by multiplying. So here I have 4 weights, specific weights, right? But you can, so 4 values, but so it means that the first interval has the mass of the further interval multiplied by 1/3 gamma, etc. Okay, so it's a standard self-similar measure. And for this measure, everything is known, right? It's a self-similar measure satisfying the open set conditions. I mean, the system is made by similarity, so everything is known. So I recall the notion of local dimension, but most of you know it. And so the fact is that such a measure satisfies the multifractal formalism in the sense that its multifractal spectrum is given by the Legendre transform of its LQ scaling function, right? And this LQ scaling function is the unique solution to this equation. It's very standard, right? It's almost the simplest measure that you can work with beside the multinomial measure, okay? And what I claim is that the analysis, in the good cases, the analysis of the function f lambda is related to the measure mu with good parameters, okay? And so let me give you the result that we have, okay? So I take a parameter in this range, okay? Square root of 2 divided by 6, 5/6. And gamma lambda is the unique solution to this equation. Okay, you can forget, I mean, you can forget about the specific value. But what is important is that now I have 4 weights, 1/3, 6 lambda plus 1/6, etc. These are the 4 weights that I use to construct my self-similar measure, right? So this is what is written here. And the fact is that, so it's important, what is important is that is point 2 right here, is that the spectrum of multifractal spectrum of f lambda is directly related to the multifractal spectrum of mu lambda. It's the same value, but translated, right? The spectrum of f lambda is that of mu lambda, but translated by this value here, okay? And in particular, it's a strictly concave function, and the maximum of d lambda is given by this value. And from this value, you can see that there is a cutting point at 1/6, because if lambda is equal to 1/6, or is below 1/6, then the log does not make any sense, right? And so it means that our analysis does not work anymore. Okay, so let's see what it looks like. So this is the spectrum in question. And so you can see that, so for different values. So you can see that there are 2 kinds of spectra, right? So every color, every value. As long as the parameter lambda is greater than 1/3, all spectra end here at a value which is log2/log3. Here, I don't, you cannot see my arrow, but okay. So all curves finish on the right-hand side at the same point. And below 1/3, then the value here increases until you reach square root of 2 divided by 6, where you see essentially there is no decreasing part anymore. Okay, so it's only increasing when you reach the limit case, right? below this limit case, we don't know much, right? The theorem, I show you again the theorem. The theorem is for lambda greater than square root of 2 divided by 6, okay? And so let me say that it's a compact statement, but there are various situations. For instance, as I said, the right-hand side is constant for a moment, and then it jumps to another value, okay? So there is, so I skip a bit, but let me just say that the mapping that maps lambda to the graph of the spectrum is continuous everywhere, except at 1/3, where it's discontinuous. So there is a phase transition at 1/3, right, depending on the parameter, which is discontinuity, which is due to the fact that at some point there is so at this critical lambda, two weights that you put in your self-similar measure become equal, and so this is why there is a jump in the dimension. I mean I cannot explain, but this is the main idea, right? And yes, so let me now explain in the few minutes that I have left. I mean 3 or 4 minutes that I have left.
3 minutes.
3 minutes. That so let me just say in a few words that indeed the local regularity of f lambda is governed by the orbit of x under the action of t. So let me go fast. So I call Mn of x the slope of Fn at x. Okay, Fn is the intermediate construction. So I call Mn of x the slope of Fn at x. And so what we have in this proposition, which takes us some time actually to prove, is that it's enough to know the behavior of Mn of x to know the pointwise exponent of x, of f lambda at x. So everything is contained in the value of this slope of the intermediary function of Fn at x at generation n. But you see, let's make some computation. So we come back. So you can look at the left part below, right? So you have AB with a slope m, okay, and we have explicit values for the two new slopes that appear. You see it's m plus 6 lambda square root and m minus 6 lambda. Okay. Let me also say that we have this picture in mind that there is a triangle with the slopes, then positive, positive, negative, positive, right? But if lambda is very small, then the left figure can happen. That you start with one slope, but then you get 4 slopes with the same sign, which is quite annoying and we don't know how to do that. Okay, and so let me just explain that the ranges depend on the fact that if you take lambda greater than 1/3, then all slopes, the slopes always increase, right? If you add the triangle, the 2 slopes of the 2 new segments are greater than the previous ones. And if you take lambda greater than 1/6, the slopes are always plus, plus, minus, plus, right? You get a triangle like that. And so, but when lambda is below 1/6, the right situation can occur and our analysis does not apply, okay? And just to explain the last minutes, the thing is that, you see, this is the formula giving Mn plus 1 in terms of Mn, right? Mn is the slope of Mn of the Fn at x, right? So it's either Mn or Mn minus something or Mn plus something. Sorry, there is a plus here, right? It's Mn plus 1. But when Mn is large, very large, right? This becomes a good approximation is like that. It's stable, or it's Mn multiplied by 6 lambda plus 1, or Mn multiplied by 6 lambda minus 1. And so instead of being very complicated, the slopes become multiplicative, right? And once it's multiplicative, then it's easy. Because in a perfect world, right, imagining that all slopes go to infinity, then the induction giving the slope would be multiplicative. And if it's multiplicative, the key idea is that the weights are chosen so that the slope is actually given by the measure mu lambda multiplied by some normalization. And this explains, right? This explains the role of mu lambda in the analysis of f lambda, okay? Of course, it does not work all the time. So I skip a lot of things. Let me just say that when lambda is below square root of 2, so in the regime where not all the slopes tend to infinity, then the formula cannot, so we only have a lower bound. There is no equality. You remember that there is equality when lambda is greater than square root of 2 over 6. But when lambda is below square root of 2 over 6, then this inequality is actually strict for many points. Right? It's only a lower bound. We know that it's not true. We have some estimates, but so it's still an open question to know what is the multifractal spectrum of these objects when lambda is small. Okay, so let's finish with the questions that remain. A lot of questions remain, actually. I mean, for instance, we don't know what the spectrum is, multifractal spectrum. We don't know whether it satisfies a multifractal formalism. We don't know if the dimension of the graph. We don't know what happens when lambda is greater than 5, 6. We don't know what happens if you put random versions or different length of the intervals and so on. So there are many things to do.